Assalamualaikum. My name is Nur Edina Shaza. I am the first presenter of Group 10. Our project title is Production of Biohydrogen using two-stage fermentation. The objective of this project is to produce biohydrogen by using two-stage fermentation. Biohydrogen is hydrogen gas that produced from biomass. Two-stage fermentation is a process that involves dark fermentation and photofermentation. The potential biomass that can be used as raw material are pure glucose, oil palm, empty fruit bunch, and grain corn. In our project, we choose grain corn as our raw material. Grain corn not only inexpensive and can be found easily, but it contains high conversion rate, which are between 94 to 97% to corn syrup. We use two types of bacteria, which are Clostridium Saccharobacter acetonicum in dark fermentation and Rhodobacter spiroides during photofermentation. Now, I will present the process flow diagram of this project. This process starts with fluidized bed dryer, which is T102. This process allows the extraction of soluble material from the corn kernel. Then it goes to T102 for grinding mills. The ground kernel will go to T10T, which is illustration tank. The function of illustration tank is to separate the starch particle. The starch particle will go through stream number 5 to go to T105, while germ, hull, and gluten will dispose as waste in T104. The starch from liquefied vessel will go to catalytic converter. The process is to break down the starch molecule, producing wide variety of glucose. Infiltration tank T106. The process is to separate the unreacted starch and sugar. The sugar produced before, which are glucose and fructose, will go to fermenter tank R102. In fermenter tank R102, the process are dark fermentation and photofermentation. During photofermentation, glucose are converted into acetic acid and hydrogen gas. The bacteria that responsible during dark fermentation is Clostridium Saccharobacter acetonicum. During photofermentation, the acetic acid are converted into hydrogen gas and carbon dioxide. The bacteria that responsible during photofermentation is Rhodobacter spiroides. TK102 and TK103 contain acid and base respectively. The function of acid and base to control the pH during the fermentation process. Acetic acid from TK106 is to top up the acetic acid during photofermentation if the acetic acid produced from dark fermentation is insufficient. The unconverted sugar during dark fermentation will dispose as waste. The next step is separation of hydrogen and carbon dioxide. It consists of absorption and desorption. At high temperature, carbon dioxide will absorb by the system and allows the hydrogen to flow out. Once all the hydrogen gas flow out, carbon dioxide gas will be dissolved by the system. The hydrogen gas is stored in TK107.
Hi, my name is Cherry. I would like to present PNID and control. Basically, our plant consists of 5 types of control. That is temperature control system, flow control system, pressure control system, level control system, and lastly speed control system. For temperature control system is to control the temperature of the during the process, that is used in fluidizer, bed dryer, catalytic converter, fermenter, and pressure swing absorber. For flow control is to control the flow rates in the pipe streams that connect to the equipment. For pressure control system, some of the equipment will build up the pressure during the process. Therefore, it is used to monitor the pressure inside the equipment. For level control system is to control the level of the tank to prevent it overfill or underfill. Uh, Lastly is speed control system. It is used to control the speed of the conveyor belt when the grain corn is transferred from one equipment to another equipment to make sure the flow rate is correct. Let's have a look for the PNID for the catalytic converter and the membrane filtrations. There are two control loops of temperature in the catalytic converter. Uh, then the flow control system between the pump and the membrane filtrations. Then have a look on the control system for the catalytic converter R101. The previous process is the corn starch is mixed with water and goes to the catalytic converter to convert the starch to glucose by glucoamylase. This process is carried out in temperature 55 degrees Celsius, where it is heated up by the water stream. This water stream are come from the fermenters and will pass through the heat exchanger to heat up the water again, then pass through the catalytic converter, and then the water will be recycled back to the fermenter. The buffer is to maintain the pH of the optimum pH of the enzyme. The first control loop is the temperature in the tank and the hot water into the tank from the heat exchanger E102. The second loop is control the temperature in the tank and the cold water out from the tank heat exchanger E101. The saccharification tank is equipped with temperature transmitter (TT) for both control loops and temperature controller (TC). Temperature controller will control the heat exchanger to ensure the temperature of the feed remain constant before entering the tanks. It also equipped with temperature alarm here at the both sides, which the temperature high alarms and temperature low alarms. Both temperature alarm will trigger if the temperature is too high and the temperature is too low from the normal situations. There also a switch connect to the alarm. This one, TSH. The switch is on or off when the temperature is too low, and the switch is switched off when the temperature is too high. Next is the fermenter control system. The first control system is to maintain the pH in the fermenter by regulating the flow rate of the inlet stream from the control valve. The control variable is pH in the fermenter, which is pH 6 during dark fermentations and pH 6.8 during photo fermentations. The suitable control structure is a speed range. This type of control system is a speed range When the fermenter process uh, pH below 6 during dark fermentations, the valve will open to allow the more base will dose to the tanks to control the pH. Then the second control objective is to control the microbes into the fermenter. XV is the on-off valve. During dark fermentations, 100 XV, this valve will open, allow the Rhodobacter species flow into the tanks. And for XV101, the valve will be closed. And for during photo fermentations, XV101 will open and XV100 will be closed. So this on-off valve will prevent the mixing of these two microbes during the process. Another control is flow control loops to control the flow rate of the acetic acid to the fermenter. When acetic acid is insufficient during fermentations, the valve 101 will open, and to prevent overdose, alarm is installed to alert the operator if the flow is too low or too high. Next control objective is to control the temperature. Here both sides of the fermenter. For the safety strategy, emergency alarm is installed in to in both sides to alert the operator if the temperature of the fermenter is too low or too high, lower than 37 or higher than 37 degrees Celsius. The temperature transmitter must forward 6 sensor code. The sensor send the code to the alarms and also activate the high or low temperature warnings. However, it will cause the emergency shutdown of the tank to prevent further damage of the fermenter. Then the next control objective is to control the level. By regulating the flow rate of the inlet stream using control valve. When the level reactant exceeds the tank level, flow indicator control will close the control valve. The last control system is to control the pressure of the hydrogens and the carbon dioxide from the fermenter during the fermentations. So when the output of the regulator sense that the pressure has dropped uh, below the predetermined point, the regulator opens and allows more pressure through. Once the pressure reaches the set point, the regulator closes and no longer allows the air to flow. So for safety strategy, emergency alarm also installed. When the pressure is high, the alarm will be triggered and alert the operator. So that's all for me. I will pass to another person to present about the job. Thank you.
Assalamualaikum and good day. I'm Nur Najah binti Ahmad. So I would like to continue for the next part for this presentation, which is hazard. In this section, we will discuss 5 part, which is deviation, causes, consequence, detection and safeguard, and lastly, suggested action. So here we can see the PNID of fermenter in production of biohydrogen. So in there are 5 strings or 5 nodes that we will discuss. In green color is node 1, in dark blue color is node 2, in blue color is node 3, yellow color is node 4, and lastly orange color is node 5. So We go for the first one, which is in green color, node 1. The stream is a stream from T106 to the fermenter that transfer glucose and fructose. We measure the parameter of flow and the level. Then we go for the node 2 color. So this is a stream from TK106 to the fermenter that transfer acetic acid, and the parameter is flow. So we to the next node is node 3 in blue color here. So in node 3, this is a stream from TK104 to fermenter that supply Clostridium during the dark fermentation process. So here we measure the parameter of flow. Then we go to the node 4, which is in yellow color. This stream from TK105 to fermenter that supply rhodobacter during the photo fermentation process. Here we measure the parameter flow. We go for the last node, which is node 5 in orange color. So here a stream from TK102 and TK03 to fermenter that supply acid and base to control the pH of R02, which is the bioreactor itself. So we go here, we measure the parameter of pH. This table shows the hazard study record sheet for fermenter R102. So here we see for the first parameter, which is flow, it can be divided into two divisions, low flow and high flow. The possible causes for this deviation, first one is inlet stream from T106 is broken. The feed line of reactant from TK102, TK103, TK104 and TK105 are broken. And also, the FIC failed to function. This may lead to insufficient of glucose to undergo fermentation process. Then it can cause overflow of glucose to undergo this process also, and the fermentation process may not be efficient. So in order to solve the problem, we install the FT10202. For the suggested action, first one, frequently maintain the control valve of each inlet stream, and also install speed sensor to control the flow of the glucose and to other feed. We go for the next parameter, which is level. In this parameter, it can divide into two divisions, which is no or low level, secondly more or high level. The possible causes for this deviation, firstly, the flow of inlet stream entering fermenter at low rate. Secondly, insufficient of reactant for fermentation process. And thirdly, the valve at the inlet stream are not functioning well. Then we see the factor. This factor can lead to slow production process. Secondly, the fermentation process may not be efficient. Fourth, the overspill of reactant, and lastly, the fermentation process may not be efficient. So, in order to solve the problem, we install the LT10201. Then, the suggested action, firstly, frequently maintain the valve at the inlet stream. Secondly, install the level alarm low to detect the low level of reactant. And lastly, install the shutdown to stop the inlet flow into fermenter. we go for the last parameter, which is pH. In this parameter, we can also divide it into two deviation, which is low pH and high pH. This deviation may cause to overflow of acid from TK103, and secondly, less flow from base from TK102. This factor may also can lead to low pH value during photofermentation. Hydrogen production rate will be lower. Secondly, high pH value during dark fermentation resulted in lower hydrogen production and may can cause the longer light time. And lastly, the high pH value during photofermentation, the hydrogen production gradually delay also. So, in order to solve this problem, we install the PHD 10201, and the suggested action is frequently maintaining the pH transmitter and pH indicator controller. Thank you.
Hi, I'm Emily from Group 10 and I will continue with the waste management of my project. The source of my waste is from the clarifier tank, which produced the hull, germ and gluten from the treatment of the raw materials. Next is the microfiltration, which produce impurities when it is filtered out. Next is the bioreactor, where the waste are biomass unconverted sugar. Lastly is the hydrogen adsorber, which produce carbon dioxide gas. Next is the industrial effluent treatment system, where we have 4 stages, which is preliminary treatment, primary treatment, secondary treatment, and advanced treatment. Preliminary consists of removal of wastewater constituent. Primary treatment is the progress of removal of portion of suspended solid and nutrients. Secondary treatment is the removal of biodegradable organics, suspended solid and nutrient. Final is the removal of dissolved and suspended materials remaining after normal biological treatment. As you can see from the flowchart, screening grid chamber and primary clarifier consists of the primary treatment. Aeration tank, secondary clarifier, and anaerobic digester is the secondary treatment of the treatment system. And lastly, the third is the chlorination, where we will treat all the waste in here. And for the air pollution, which is carbon dioxide gas, we will use carbon capture and storage treatment for that. The carbon capture and storage, CCS, is capturing and storing of carbon dioxide before releasing into the atmosphere. Once carbon dioxide is collected, it is compressed into liquid state and transported by pipeline, ship, or road tanker. Carbon dioxide is then pumped into underground, usually 1 km, to be stored into depleted oil and gas reservoirs and coal beds. The air pollution will cause climate change and cause impact on the public and individual health. The source of air pollution in my factories are the production of carbon dioxide gas and dust. With this, we will use the varieties of technology to destroy the air pollution at the source before releasing it to the atmosphere. And besides that, we will use sustainable raw material, which is grain corn, for our raw material. Next is our noise pollution, which it will cause health problems such as permanent hearing loss on the workers. The source of the noise pollution are the process of grinding mill, the operating pump such as centrifugal pump and air compressor pump, the operating hydrogen adsorber, and the motor parts and rotating parts of the equipment. We can eliminate the noise source by adding acoustical material to the noise radiating surface, and earplugs or ear muffs are kept for the workers when working. Lastly, we will discuss on the economic assessment of this project. We will use percentage of delivered purchased equipment cost ratio factors. Our total capital cost estimation is 1.432 billion, and our total raw materials used is 1.52 million per year, and our annual operating cost is 0.093 million per year, where this will contribute on 2.230 million per year on the total production cost. On the other hand, 3.40 million of biohydrogen production is produced per year. On the economic evaluation on constant inflation, our ROI, which is return of investment, is 22.5%, and our payback time is 2.8 years. For the economic evaluation of 2% inflation, our ROI is 25.8% and our payback time is 2.5 years. Hence, there is an advantage on the production of biohydrogen. It could use as a primary source of energy in the future. From the Petroleum Development Act 1974 to the most recent Fuel Cell and Hydrogen Blueprint 2017, it shows that Malaysia is ready to embrace the renewable resource as energy source. Hydrogen also can play its role in the electric supply industry. Hydrogen also excels in power generation in both portable and importable source. Hydrogen is also a more economical fuel. On such uses of hydrogen, it is undeniable that production of biohydrogen takes a leap forwards on the future. And that is all for our project. Thank you and stay safe.